So welcome everyone to the Temerty Center speaker series today. It's my pleasure to be facilitating this conversation. My name is Amol Verma. I'm one of the Temerty professors of AI Research and Education in Medicine at the University of Toronto. It is my pleasure to be able to facilitate our fantastic speaker for today, Dr. Jessilyn Dunn. Before getting started with her introduction, we wish to acknowledge this land on which the University of Toronto operates. For thousands of years, it has been the traditional land of the Huron-Wendat, the Seneca, and the Mississaugas of the Credit. Today, this meeting place is still the home to many Indigenous people from across Turtle Island, and we are grateful to have the opportunity to work on this land. The Temerty Center for AI Research and Education in Medicine at the University of Toronto has been made possible by the generous donation of the Temerty family. T-CAIREM is an interdepartmental center, and it serves as a focal point for collaboration among healthcare providers, trainees, researchers, computer scientists, engineers, and industry. Our goal is to transform health through AI. I'd like to just mention that this event is accredited for continuing professional development. In order to obtain your CPD credit, please complete the evaluation form that we will email to all attendees following the event, or you can use the QR code on the slide that will be posted at the end of the presentation. And don't forget to provide your name and email address on the evaluation form so we can log your CPD attendance. Through the session today, please use the Q&A function in Zoom to submit your questions to Dr. Dunn, and she will address them during the discussion portion of the webinar. By attending this event, you consent to being photographed and recorded for non-commercial use by T-CAIREM. The event is also being live tweeted, so please follow along using the hashtag TemertyTalks. Okay, so it's now my great pleasure to welcome Dr. Jessilyn Dunn, an assistant professor of biomedical engineering and biostatistics and bioinformatics at Duke University and director of the Big Ideas Laboratory, whose goal is to detect, treat, and prevent chronic and acute diseases through digital health innovation. Today, she will discuss how recent digital health technology makes it possible to closely and continuously monitor individuals using multiple measurement modalities in real time. Her team is collecting and integrating such wearables data with clinical information to gain a more precise understanding of health and disease and develop actionable predictive health models for improving cardiometabolic and infectious respiratory disease outcomes. Dr. Dunn, over to you.
Thanks so much, Dr. Verma, and the entire Temerty team for inviting me to speak at this series. I will go ahead and share my screen and get started. So I'll just be sure that you're seeing a full screen rather than notes.
We are seeing the notes right now.
You're seeing the notes, okay? How about now?
All right, you're all good.
Full screen. Okay, great. So just to get started, I have the only conflict to disclose is that I'm a scientific advisor to Very Inc. I want to mention the learning objectives for today's talk. First, the goal is to learn the definition of a digital biomarker, and then to understand the data supply chain for wearable devices, and I'll talk about what that means. Learn methods to evaluate wearable devices and the data that comes from them, and then to explore real-world applications of digital biomarkers. Today, I'll be focused on one real-world application, which is the detection of upper respiratory infections. There are many other real-world applications, some of which I will allude to, but won't have time to go into great detail on. So the motivation for the work that we do is that there's this ever-expanding breadth of different methods to monitor biosignals. So we have a variety of on-body locations. We have environmental sensors that can also measure and monitor health, things going on outside of or inside of the body. And these technologies are expanding such that they're becoming seamlessly integrated within our daily lives, moving from things like smartwatches on our wrists to smart clothing that can be worn every day without noticing that it needs to be charged or that it's actually sensing anything. And so you can see on the screen here, there's an example of painted on electronics, right? So something like a tattoo electronic, where you wouldn't even necessarily be wearing anything or notice that something is on your body sensing. And so what this leads to is this large opportunity for continuous monitoring of health. One of the challenges that comes out of this, though, is that there's a lot of data that we have to learn how to use appropriately such that we can make informed decisions about how to intervene and improve human health. So during this talk, at the bottom of the screen, I'll have this roadmap. So we'll start with talking about what digital biomarkers are, we'll talk about challenges, and then we'll talk about that application area of infection detection. So my lab at Duke is the Big Ideas Lab, which if we're in the healthcare sector, we know has to be an acronym. And so it does stand for something. And it's essentially who we are, the Biomedical Informatics Group. And what we do is integrating data engineering and analytics. So what this means in practice is that we're aiming to develop and test tools and infrastructure using biomedical and health data for early detection, intervention, and prevention of disease. Now, that's a very large goal. So within that, we have a lot of specific focus areas that we're working on. In order for us to discuss those in detail, we'll first talk about what digital biomarkers are. So if we think back to the traditional sense of a biomarker, we have kind of these two overarching uses that biomarkers have. The first is diagnostic capabilities, and the second is teaching us new things about physiology. So if we think, for example, about in the diabetes realm, we can consider a blood biomarker to be fasting plasma glucose, or blood glucose. And we can use that as a diagnosis method. So we can take somebody's FPG, glucose, and see whether it is above a certain threshold that would place somebody into a prediabetes or type 2 diabetes category. We can also institute lifestyle changes or medications for people who may fall into those categories, or preventative measures for people who don't, and use FPG as an intermediate marker of disease. We can also use that same biomarker to track treatment progress. So if we institute one of these changes, is it actually making a difference? Is it actually doing the thing that we hope it would do? So these are sort of the known biomarkers, but we also have this interesting ability to discover new biomarkers. So if we think about these large-scale omics studies that allow us to explore the genome, microbiome, proteome, metabolome, and find new associations between biomolecules and disease states. That allows us to learn something new about physiology. So for example, we may discover that there's a new gene that hasn't been found before to be associated with type 2 diabetes, but a new study in a new population uncovers that relationship. We can start to actually uncover mechanisms behind phenotypes and biological function, linking them together through this biomarker, and can even then leverage that to develop new drug targets. So biomarkers are an incredibly useful resource for us, both for healthcare today, as well as developing new technologies for the future. So the reason that I'm reintroducing this concept of biomarker is because when we think about a digital biomarker, it follows exactly the same principles. So the only difference is that rather than taking a biosample, like a blood, urine, fecal sample, tissue sample, or so on, we're taking a digital sample, a digital measurement. So the definition that we use for a digital biomarker is digitally collected data. So this could be, for example, continuous location data coming from a smartphone GPS that we transform into an indicator of health outcomes. And this indicator can be used in all of the ways that I described previously for our traditional biomarker. So putting this mathematically, what we're trying to do is take a series of continuous measurements that can be collected from sensors on the body or in the environment that we transform through mathematical transformations in order to predict this target outcome of interest. And these are more traditional measures that we may be more used to seeing in the clinic. So clinical measurements, like our example, fasting plasma glucose, that could actually go on this target outcome side. So taking in these new data types building predictive models such that they are representative of our existing notion of disease, as well as potentially teaching us new things about disease with some unsupervised learning methods. So this is the supervised structure of learning. And then we also can just look at trends and relationships within these variables to discover new biomarkers. And we've been doing this in a variety of ways in my group, and you can imagine the application areas beyond this. So we start with the question, can we develop digital biomarkers to detect or predict when we're talking about infectious disease? We talk about how contagious a person might be if they already have an infection. If they don't have an infection, what might be their susceptibility to contracting an infection if they're exposed to the pathogen. We're looking at lifestyle diseases like pre and type 2 diabetes and general health effects of exercise, sleep, diet, and different sorts of lifestyle changes. We are exploring how circadian disruption, for example, in shift workers impacts overall health. And we're doing studies in women's health that are a combination of looking at physical and mental health. So with that as a backdrop of what are the opportunities in developing digital biomarkers, I think it's important for us to also understand the challenges that are associated with digital biomarker discovery. And there are a lot of them, but they're all quite addressable in a lot of different ways. And so one of the take-home messages that I hope comes from this talk is that this field really takes a community of researchers who bring varying expertise to the table in order to tackle all of these different challenges. So this is a non-exhaustive list, but essentially this is kind of the major challenges that we see in our work on digital biomarker discovery. So the top three are the areas that I will discuss in more detail, and the bottom two are large enough issues that could stand to each be their own 1-hour talk. So I will talk about our work in device and data validity and accuracy, and how we can assess devices and data to ensure that they are fit for purpose. We also have this challenge, and this is a broader challenge not only in digital biomarker discovery, but also in AI and machine learning more generally, which is interpretability and FAIR principles. When we develop models from data, making sure that others can understand what the model is doing and that these models abide by these FAIR principles, which means that they're findable, accessible, interoperable, and reproducible, such that the data and the code are available to be explored and understood. Given all of these new sensing modalities, we're running into this issue of a data deluge, which isn't new, but is only growing in the challenge of how to bring all of this data together and crunch it in a way that's actionable in a timely manner. So I'll talk a little bit about some of the methods that we are developing to try to address this. And with regulatory oversight, we have a variety of different regulatory agencies, from the US FDA to the European Medical Association and beyond, that are trying to learn as this field evolves how to best explore and understand the devices and inform the public and our clinical folks about how best to use and interpret the data. And then we have a variety of what we call ELSI, ethical, legal, social implications, and privacy and security issues as well that all need to be addressed. So when we talk about looking at the accuracy of devices, we have this challenge where a lot of the devices that we use will have, something written on the box that says this is a clinically validated technology. But unfortunately, there's not a clear definition for what clinically validated means. So this is very confusing to not only consumers, but also clinicians who are trying to interpret data that their patients bring to them from devices that they may have purchased as consumer technologies. Prior to the work that we did with the Digital Medicine Society, there was really a lack of a systematic evidence-based evaluation framework for these tools. And one of the challenges is that these tools aren't just a single tool that have a sensor and an output, but rather there's a lot that goes on the device itself and on the cloud that processes the data to give some sort of an outcome that is supposed to be actionable. And so when we talk about the data supply chain, which we'll go into more detail on the next slide, we have to consider how the data flows from the actual sensing mechanism all the way to the output from the device, and how that flow should give us some pause when we're thinking about the provenance of the data, where the data comes from, how it may get manipulated over that supply chain. And then finally, I'll talk about this framework that we developed called V3, which is a verification and validation process that is ensuring that a technology is fit for purpose. And we'll talk through an example of that to really make this concrete. So in thinking through our typical wearable, we can take a look at something that appears to be a common consumer wearable device, your Fitbit, Apple Watch, Garmin, Samsung, Microsoft Band, whatever it is, a wrist-based wearable that has an accelerometer on it. So oftentimes, most people think of the accelerometer as measuring step counts and don't really think much beyond that. But what's really going on under the hood is that we have a sensor, this accelerometer, that actually is transferring a physical motion into an electrical signal that is then transformed into something like a step count. And the way that that works is through this data supply chain. So we have a physical motion that gets sensed often by an accelerometer that has two capacitance plates that, when there's a high acceleration, get closer together, that transfers energy and leads to an electronic signal. We have this analog to digital converter, and then these signals get transformed through microprocessors in order to process those signals to be smaller so that they don't take up quite as much space, to be transferable, for example, over Bluetooth, and that can be transformed into something like a step count. So when we say raw data, I think it's something to be really thoughtful about, because we can mean a lot of different things when we mean raw data. And oftentimes we get a question in working with these wearable sensing technologies: can you show me what the raw data looks like? And I think, this is an area for us to be very thoughtful about, which is, when we call our data raw, we should be thinking about what actually generated that data. And were there processing steps that may have actually changed the signal level data? So sometimes we will refer to the sensing method that actually generates that primary signal as the signal level data. But really getting specific in the language when we talk about raw data is really helpful in order to understand the provenance of the data, where it comes from, where it may have changed along the way, and how, if you're developing digital biomarkers, those changes might actually affect the models that you're building and the digital biomarkers and what they recommend. The other piece that's important to consider is how accurate the technologies are for the purpose that you intend to use them for. So the example, if we continue along this idea of an accelerometer, we've got different ways to evaluate this technology. We can start on the benchtop and say, if we put this accelerometer on a shake plate, we expect that it would report back a certain RPM. And that would be sort of our benchtop in-lab verification of the technology. But we know that when we move that sensor to a real person, oftentimes there are other challenges that come into play, different sorts of artifacts from different kinds of movements or environmental variables that change the way that sensor might perform. So we put that accelerometer on a real person, and against the gold standard would measure step counts. So for example, we would have somebody who's actually counting steps, which is the gold standard method, while we have the accelerometer on the person. And then the last step is, if we want to use this sensor clinically, we want to make sure that it works for the population that it is planned to be used in. So although this accelerometer might be really great at measuring step counts in an average healthy person with a normal gait, if we put it on patients, for example, with MS, who have a different sort of gait pattern, the technology may not work the way it was intended. So it's important to go through this last step of clinical validation anytime the technology is aimed to be used in a different population, and ensure that it really does measure what we intend it to measure. And part of the reason that this is iterative is that there are changes that can occur to these technologies, particularly the consumer devices, where there may be over-the-air updates that change the step count algorithm or the heart rate algorithm or the irregular heart rhythm algorithm. And every time that that happens, it's important to ensure that the device is still doing what we expect it to do. And we want to make sure that if we're ever moving from one population to another, that that hasn't changed so substantially that the device may actually fail to do the thing that we expect it to do correctly. So this is challenging because we don't always have all of the information from companies about changes to firmware and changes to the underlying hardware when we have new versions of devices. So this is still an area that requires more progress and requires more talking with companies and regulatory agencies to ensure that we have the information that's needed such that we know the technologies we use are fit for purpose. So one thing to consider, and this is something that has become more of common knowledge over the past several years, particularly during the COVID-19 pandemic, is that if we think about our methods to measure heart rate or blood oxygen saturation, these are typically optical measures. And the way that they work is that there's an LED. So if you have a smartwatch, the green or red light on the back of the watch is that LED. It emits light. That light gets absorbed through the tissue, and that absorption varies depending on the blood underneath the skin. And then whatever is reflected back or whatever is not absorbed is detected. And that's how we get heart rate and blood oxygen saturation measurements. The challenge that has come up is that these technologies were found not to work equally well across all skin types. And so this is a real challenge because the individuals that the devices were tested in were not representative of the individuals where the devices were deployed. And this, for heart rate monitoring, has a variety of different sources of problems. So we have this detection across diverse skin types, which I'll talk about a little bit more. We have issues with optical motion artifacts. So the devices may not work as well for somebody who is moving quickly as for somebody who is moving slowly. Different locations on the body have different perfusion levels and therefore work better or worse. And some of the algorithms that sit on the device are intended to pick up periodic signals. So there can be crossover issues where if there's a heart rate at a certain cadence and a walking pace at a certain cadence, those signals can actually get mixed and confused. Going back to the skin tone issue, the idea here is that this light would be absorbed mainly by hemoglobin, by oxy or deoxygenated hemoglobin. But one of the challenges is that green wavelength of light that's typically used also gets absorbed by melanin. And so the more melanin that a person has, the more that light gets absorbed, the more difficult it is to obtain a good optical signal. So that's a challenge that wasn't known until problems started to come up clinically. And this is really more of an issue with improper verification and validation at the outset. So in my lab, we performed a study to explore the various challenges associated with some of the common consumer wearables and common research grade wearables that were available at this time. This was roughly 5 years ago that this study was done. What we found was that for the devices that we measured, we actually did not see major changes in accuracy based on skin tone, which was a reported problem for prior versions of these devices. So there were some changes that the companies had made in order to tune up the LEDs to address that. But one issue that we did see was that during high activity levels, the accuracy of the heart rate monitors went down dramatically by roughly 30%. So if we think about what that means in a study where, for example, you're doing an exercise test, all of a sudden the data that you collect at rest has a different level of accuracy than the data that you're collecting during the exercise. And that's very problematic because for people who don't know about these differences in accuracy, they may come to conclusions that either there's no difference or there is a difference in this population between rest and activity that may not actually exist. So this is just to drive home the point that appropriate verification and validation of these devices is critical in order to then use the data for digital biomarker development. I'll continue on and happy to answer any questions if they come up. Just feel free to sort of unmute or put in the Q&A, and I'll be glad to pause at any time. So diving into actually using this data. So we have some challenges in, how we can go about sort of sharing learnings in this field in order to create digital biomarkers that can be evaluated by the broader community and updated and improved. So one of the things that my group is working on with the broader scientific community is this Digital Biomarker Discovery project. So if you want to check it out, you can go to dbdp.org and you'll see more information. But essentially, the idea is to open source a lot of the modular methods that are developed in the digital biomarker discovery space. So we have data sets that can be used as benchmarking data. So if multiple different researchers develop step count algorithms or heart rate algorithms or diabetes detection algorithms, these could be tested against various data sets to ensure that they work as intended on different populations. And that code also is made readily available along with the algorithms that underlie that code. And then finally, the development of educational resources. So this is, again, broadly a community effort, and anybody who's working in this space is really encouraged to check out the DBDP and learn how to become a contributor or ingest the resources and maybe one day in the future become a contributor. But the educational resources really enable learning about digital biomarkers from the ground up. So somebody who may have no experience in the sensing technologies can still gain a lot of sort of base knowledge to get started in this field. So some examples of code modules that we and others have developed that exist on DBDP are data preprocessing, methods to explore data. So if you have a large influx of data coming in, for example, heart rate measured every minute for 6 months, a lot of times people ask us, well, what do we do with this data? So we have some methods just to get started visualizing and understanding trends in the data. And there's a variety of different modules that exist. And if you have developed a module that you think would be useful for others to use, we really encourage you to add your own module here. One module that I'll talk about a little bit is our data compression toolbox, which is relevant to one of the challenges, which is the data deluge, the major amounts of data that are coming in. And there's a lot of documentation here. So, the aim is with this open source software platform. We've been funded by the Chan Zuckerberg Initiative. We're continuing to be funded by the NSF and beyond, and really making this accessible. So again, please do check out the resources. Please do let us know what you find useful, what may not be so useful, where you could envision expansion. And the community in the DBDP is really excited to make this resource useful for the community. And so revisiting this idea of these massive amounts of data and how we may be able to use data compression methods to improve how we deal with massive amounts of data, setting the stage for this problem. So this is an older statistic, I guess, because we are now past 2020. The amount of data was projected to have exceeded 2,000 exabytes. And essentially that is equivalent to 2 trillion gigabytes. And the cost associated with that amount of data is anticipated to be roughly $7.2 trillion. So a huge amount of data leads to a huge footprint. Not only is it a cost footprint, but we also know that there are environmental footprints associated with processing these large volumes of data. So one thing that we've been quite interested in is, well, how much data do we really need to collect from these sensors? Because when we talk about this raw or signal level data, you can imagine that you could keep increasing the sampling rate. And in engineering, we have this, this notion of the Nyquist rate, which is sort of the minimum sampling rate that you need to observe the phenomenon of interest. However, in a lot of this discovery work, we don't always know what the phenomenon of interest is. So there's a lot of exploratory work, and a lot of our colleagues will say, well, then let's sense at the maximum sampling rate we can. The problems with that are these huge data volumes, and then also battery consumption on the devices themselves. So a lot of the work that we've been doing is trying to optimize sampling rates such that we can get to the phenomena of interest without creating these massive data footprints. And so the way that we can work to reduce these data volumes is first reducing the amount of signal level or raw data that we collect, and then second, developing application-driven compression methods that work specifically well for biosignal data, such that we can preserve the integrity of the data that we're working with for digital biomarker development. And we know that different compression methods can really make or break that downstream data. So anybody who, for example, has compressed an image before, and then you try to open it back up and it's really pixelated and granular, that is a compression method that is not well suited for the image compression task. Similarly, there are a lot of data compression methods that are not well suited for the biosignal task. So that is one of the areas that we're working in. And then finally, we can intelligently aggregate data together. So when we have duplicative signals, or when we have methods to bring different data types together to get a better picture of health, that's an option to compress data in a knowledge-driven way. So in a way to develop these indicators of health by crushing down data. And an example of this is a down signaling study that we developed, where essentially what we were looking for is, we have these very high resolution ECG data that are collected in the clinic, typically at somewhere between 400 and 1,000 hertz. If we were to collect that high of a sampling frequency on a smartwatch with an LED, it would kill the battery pretty quickly. And so on a PPG, it's actually not necessary to collect data at that high of a frequency if our interest is in getting heartbeats, for example. So we can see that on a PPG sensor, we have these peaks that can tell us where there are beats. So if we were to even lower that sampling rate, we would still be able to recognize these peaks and get heart rate. But for example, we would be missing information that might be able to be detected at higher sampling rates. Like, for example, some irregular heart rhythms, where we would need the additional detailed either electrophysiology or more detailed blood volume changes that indicate backflow or something like that. So the question became, how do we downsample the data in a way that is fit for purpose for the question at hand? And one of the areas of interest for our group in working with mental health as well as prediabetes is using heart rate variability. And what we found is that we can actually reduce the sampling rate on a wrist PPG sensor by a sort of dramatic amount. So going from 64 hertz down to, for example, 21 hertz, still maintains the original HRV values, heart rate variability values, but doesn't have this huge data footprint. And why this matters is because this translates to real dollars. If we are to look, for example, at the data storage requirements for 24 hours of monitoring data measured at either the ECG level of 1,000 hertz wearables data at 64 hertz or the decreased level at 21 hertz, we can see that the cost translated from that decrease goes down by more than half. So as we are increasing the amount of data that we collect, it's very important for us to think about what will be the storage footprint, what will the cost to compute on this data be, what will the time cost of actually opening and processing this data be, and knowing the appropriate compression method or sampling rate is important. So to take that one step further, once we have the data, we have it at the appropriate sampling rate, we can further condense it down by leveraging compression methods that are appropriate to the data type at hand. So another study that we did went through various methods of data compression and compared them across the different types of biosignals, which have different structures of their signals. So for example, we have periodic signals. We have signals that tend to be pretty stable. And these different types of signals are best optimized for compression in different ways. So what we found was that looking at these two target metrics of PRD, or percent root mean squared difference, or compression ratio. So we want the difference from the original data to the compressed data to be as small as possible, and we want the compression ratio to be as high as possible. There are various compression methods. We can combine those with multiple encoding methods. So trying permutations of transformation plus encoding methods led us to an optimal data compression pipeline for different data types. So the take-home message from this work, and if you're interested, I encourage you to check out the paper here, is that there are methods that are most appropriate for periodic data, the direct data compression plus Huffman encoding, using electrodermal activity and accelerometry, which have a different sort of data structure, a more tailed data distribution rather than a normal distribution. SVD and Huffman encoding was the most appropriate. And for skin temperature, we have bio-orthogonal discrete wavelet transforms with Huffman encoding. So the take-home message is that there are different methods to crunch down this data so that it has a smaller footprint and can then be stored and accessed later on without a huge cost to the study team. And we have these data compression methods available on the DBDP. So last but not least, in the last roughly 5 to 10 minutes of this talk, I want to talk about applications of digital biomarkers. And a lot of times for our clinical partners, this is maybe some of the most exciting work that is most applicable to real people in the real world. So this work stemmed from a study that I collaborated on as a postdoc at Stanford with Michael Snyder, where there was a longitudinal profiling that was done over about 100 people over the course of several years. Now the study is going on more than a decade. And people were coming into the clinic regularly during these years of monitoring to have samples taken 4 times per year. But what was interesting is because people were out sort of living their normal daily lives, there were natural perturbations that would take place, like infections or stressful life events or dietary changes that people would undergo. And during those times, we had higher resolution sampling. So people would come into the clinic more frequently to give samples for traditional biomarker analysis, multi-omics data analysis, as well as wearing a wearable device throughout the entire period. So wearing the wearable not only during the clinic visits, but also during the time between the clinic visits. And if we hone in on the data from people who wore the device regularly, we've got a subset of 43 people. So on the x-axis here, each of these ticks is a different individual. What we can see is that across all people, we see sort of a typical heart rate value, a typical skin temperature value, and what becomes immediately evident is that we have lower variance in our skin temperature across people than we do in heart rate. which makes sense given what we know about body temperature's dynamic range versus heart rate's dynamic range. But what's really interesting about this is that if we look at two people who have the same average heart rate, so for example, we've got this person here, and we can compare them to this person here. Now, if we are to look at a value for this person that's roughly close to this blue triangle, hopefully you can see my mouse, that value would be within a normal range for this person, given that person's high intra-individual variance. However, for somebody with the exact same resting heart rate average, that value for resting heart rate would be well outside of their norm. And so what this sort of indicates is that a single average or a single point in time measurement is not enough to really capture what is normal for a particular individual. And therefore, monitoring, for example, resting heart rate over time is not super useful when we only have maybe one clinic measurement every several months. And that's why a lot of these measurements tend to only be used for triage, for emergency care, but don't actually allow us to learn things about people's physiology over time. And these intra-individual differences hold true across parameters that we might not normally think are key to measure. But for example, we have changes over circadian patterns. We have decreases in resting heart rate at night that differ by individual. We have increases in skin temperature at night. And we can see that these changes vary for different people. So we might be able to begin to leverage the norms for an individual in order to detect anomalies. And that's exactly what we did, is we designed this method that we call change of heart, which was essentially taking these continuous measurements. It was measurements at 64 hertz. So we have really high resolution measurements, and we can bin them into daily bins that say this measurement is typical for this person for this day, or this measurement is abnormal for this person for this day. And this enables us to look over a pretty long time span at an individual to find blips on the radar. So to find things that fall into this really high bin or this very low bin where measurements are well outside of the range, and we can account for outliers and noise by looking at sort of the size of that bin, how many outliers there are during that day. And an example from a real participant in our study is showing some blips on the radar. This is monitoring over 6 months at a resolution of 64 hertz. This blip on the radar, where we have a very high heart rate, corresponded to a Lyme's disease infection. And what we could do is find the blips on the radar, go back to the electronic health records, and we saw, because these people were coming into the clinic regularly and even more frequently when there was an illness, we could see this increase in white blood cell counts and the positive test for the Lyme's disease antibody. So this is just kind of one example of how this continuous wearables data can be used for continuous monitoring of infection. For the same person, though, this is a really interesting method that we could layer on top of the study, because people were coming into the clinic to give healthy samples as well as samples when they were sick. So all of the points on this plot here correspond to days when this person came into the clinic to give a sample. And on the y-axis, we're looking at the proportion of skin temperature outliers, and on the x-axis, we're looking at the proportion of heart rate outliers. So the more outlying measurements here, moving to the upper right-hand corner, are measurements that are more abnormal for that individual. And for each of those, we have corresponding clinical measurements. So the most outlying measurements from the smartwatch data corresponded to that Lyme's disease infection that I showed you with that blip on the radar. But there are, interestingly, these other outlying observations. So we looked back at the records for this person and saw that one of these outliers did correspond to a viral infection, but 2 other outliers corresponded to days where there was high C-reactive protein, which is an indicator of inflammation. And so what that really indicates is that the smartwatch measurements were able to detect that there was inflammation, that there was something abnormal going on these days when the person didn't report any symptoms. They didn't even know that they had any level of inflammation, but it was detected through the smartwatch. The question may become, well, what might we want to do about that? Is that always useful knowledge to have? Could it lead to overtreatment, for example? Well, when we start to think about pandemic preparedness, actually, there's a lot of value in looking at pre-symptomatic or asymptomatic levels of inflammation. And so just to make sure that we've got enough time here, I want to skip ahead a few slides and just talk about how we might leverage the information from devices like smartwatches and smartphones to know when somebody might actually be sick before they may even know that they're sick. So we have our traditional measures of sort of case investigations, of surveillance testing, contact tracing, epidemiologic surveillance. We've got public communications, vaccine treatment and development. And our smart technologies give us a huge opportunity to begin to come up with new methods that will better serve our community during future outbreaks of novel pathogens. So we developed during COVID-19 early on this Cove-Identify study. And the questions that we asked were, using smartwatch data, can we learn who should be quarantined or tested for COVID and when, and who might need specialized care resources and when? And our goal was to use the smartwatch data to develop digital biomarkers of susceptibility to infection, whether or not somebody currently has a COVID-19 infection, pre-symptomatic or early signs of infection, how contagious they might be if they are infected, and begin to differentiate between different types of respiratory infections and explore illness trajectories. And one of the applications that we were most interested in here was whether we could improve the allocation of tests to people who might need them most. So if you recall, during COVID-19, there were a lot of testing shortages wherein lots of people were getting surveillance testing, but there was lots of surveillance testing for negatives rather than aiming to capture those who were more likely to be positive. So we developed this method that we call ITA, or Intelligent Testing Allocation, where we leverage the information coming from a smartwatch to add a statistical prior to the likelihood of somebody being positive for COVID-19 before a test goes out. And the motivation for this is, say that we have a group of people where we have fewer tests than we have people that we would like to test. In this picture here, we have the orange people who are COVID positive, and we have the blue people who are COVID negative, but we don't know this information until after the testing happens. So we've got a subset of tests that we can distribute over this larger population. What we found was that we can leverage the data from smartwatches to improve the positivity rate of testing so that we capture more positives. So the difference is, if we were to do random testing, we would capture one of these orange people, but in the addition of the priors from the smartwatch, we can now capture 4 of the positive cases. So the way that this works is that we are looking at the difference in the digital biomarkers between people who do and don't have COVID. And I'm going to go back a second here just to show you at a high level. We see that for people who have COVID, we have a decrease in step counts, and we have an increase in resting heart rate prior to the occurrence of this test date. So what we aim to do is optimize this baseline and detection period such that we know when we can start to insinuate that somebody might have COVID-19 based on changes in their smartwatch data from the baseline. And we performed this very extensive grid search in order to be able to discover the optimal time frame to look at these differences per different types of digital biomarkers. So looking at physical activity features, looking at resting heart rate and heart rate related features, and then looking at a combination of detection window lengths and the detection end date. So how close to that test date do we want to get? And if you'd like to know more details about how this was all done, this was published by my postdoc, Mobashir Shandi, in MPJ Digital Medicine. The key results from this work is that using the ITA method, we could generate a 6.5-fold increase in the positivity rate of our testing. And, we have a 6.5-fold increase in our cross-validated training set, a 4.5-fold increase in our held out test set. So what we think is the most important take-home message is that we could actually capture asymptomatic individuals. So up to 27% of the positive tests that came back were for people who were otherwise reported to be asymptomatic. We use resting heart rate and physical activity features, and depending on the timelines, different features were more relevant for different aspects of disease detection. And the different features also enabled us to tune the false positive and false negative rates for this work. And on a larger scale, we could envision that this would be useful for epidemiologic surveillance. So this group at Scripps had done a United States-wide exploration of a comparison of Fitbit data versus CDC flu reporting, and showed that you can actually see trends in flu outbreaks from Fitbit data before the CDC actually gets the reports from the local public health agencies. So there's a huge potential here for this technology. So with that, we can summarize the talk from today that we have this definition of digital biomarkers, that we have digitally collected data that gets transformed into health outcomes. And there are a variety of underlying challenges there that cause us to sort of really need to think in detail about how to leverage this data. And then one example of a real world application is using digital biomarkers as early indicators of respiratory infection to inform resource allocation. There were a lot of people who contributed to this work, and I would be remiss not to thank not only my group, but our various funding sources, as well as all the contributors to the DBDP. That I'd be glad to take any questions, and thanks again for the opportunity to present.
Thank you so much, Dr. Dunn. That was so fascinating. And so the Q&A box is open if anyone would like to submit questions. We do have a number of questions that were actually submitted in advance. I might actually start with a question related to clearly your work is oriented towards building an open source community and focusing on the academic research side. I'm curious how that sort of philosophical, methodological tooling approach has intersected with the need to work with the vendor community on the wearables, and how open the vendors have been. You spoke a lot at the beginning about the need for the initial validation and verification of how signals are processed, acquired, transformed, etc. How has that process been, and are the vendors sort of happy to allow you to open the vault and be transparent about some of those early steps? And would love to just sort of hear your experiences there and where you think the field is going.
Yeah, so I'm glad that you asked this question, because I think this is a really good point for the broader community to be thinking about the tools that we actually decide to use in our studies. Because we have choices when we put in a grant of, are we going to be using some commercial off-the-shelf wearables? Are we going to be using wearables from research companies? And there are pros and cons. And, a lot of times what we're balancing is the usability of the technologies and the devices, how enjoyable it is for our participants to use, with how open the companies are to actually accessing the data, the different levels of data, whether it's that signal level data versus the more processed data. And then there are technological limitations that are also inherent to some of these devices. So there are a lot of considerations in actually choosing the device to use. And I think, there is this sort of push and pull that companies are interested in developing algorithms themselves as well. And there can be some sort of crosstalk and cross-pollination and collaboration that comes out of the research that we do when it's set up properly, that incentivizes both sides to really be open and transparent, that sort of everyone can win. And that's, again, not always the case. So just being really thoughtful about the vendors that we work with, and asking the community members who have worked with different vendors before, who has been more open, and hopefully that does start to incentivize vendors to get on the train of being a little bit more open, because then more researchers use their devices, come up with new algorithms that are then used in practice. So, I think that also can be part of the conversation with vendors of incentivizing them to play nicely with us.
Yeah, and maybe picking up on that There's a question in the chat that relates to how do you ensure that the digital biomarkers you develop can be used across different vendor solutions, or how much of that is an aim of your work, or do you just acknowledge that maybe that's not always possible?
So that's a great, that's actually, we have a recent R01 where that exactly is the aim, which is that we've developed a technology that works in a particular research grade smartwatch, the Empatica, and we are trying to transfer the knowledge that we've developed on this research grade device to the broader ecosystem of different commercial wearables. It's tricky because not every wearable gives us the same types of information. And so we have some commonalities. We know in general, wearable devices have accelerometers and PPG sensors. So from there, we can say, okay, we can limit the digital biomarkers that we're focused on to those universal sensors. But again, we want to choose those that we can access the raw data. And not every device lets us do that. So I don't think there's a one size fits all answer here. I think it's more of, if we're developing something that uses heart rate and steps, that's very straightforward. That can go across a variety of devices. If we're using something that uses the curve of a photoplasmography, the PPG, that's a little bit more tricky. So using these more aggregate measures can help.
Yeah, perfect. Thanks. Some of the applications you alluded to involve the integration of wearables data with maybe other types of healthcare data, like EHR data, whether that's to collect outcomes or maybe to assist with your prediction and other work. Can you speak a little bit about that process and how you see wearables integrating with the broader ecosystem of electronic health data? A lot of the EHR solutions are not particularly open in terms of connecting and integrating data with these. So where do you see what has your experience been there, and where do you see that go?
So this is a real challenge for implementation in a clinical setting. The EHRs that we have designed today are not structured in a way that is friendly to ingesting wearable device data. Some of the use cases that we've been sort of playing with the health system here at Duke and beyond is continuous glucose monitoring data, because that gives, for example, like daily summary metrics that can maybe be ingested in a slightly more compact format. But still, one of the big challenges that we hear from clinicians is that I don't have time to look at a time series of data over weeks. Like, I want a single number, or even just like a red alert, green alert that says these patients are fine, these patients are having challenges. So when we think about continuous glucose monitoring, for example, we could have a single metric over the course of the week that says, this patient has a red light. They've been out of range, 60% of the time this week, whereas these patients are green light. They're mostly having high range. We could also consider it for sleep. Right? We get a lot of information about sleep from these devices, and we could have a red light. This patient is clearly having some kind of insomnia, whereas green light, these patients are sleeping in a typical way for themselves. So that's one of the things that we're trying to work on with this idea of digital biomarkers, is really compressing the information to be actionable. There's no need to flood the EHR with this really high resolution data when that's not what the clinicians want to see anyways. So that's some of the work that we're doing now.
Perfect. Thank you so much. Maybe in the last minute, I'll just ask you to speak about where you see what's exciting for you on the horizon, new applications. Maybe there's a question there about integrating new other sort of molecular biomarkers as well as digital biomarkers. So curious if you could just give us sort of a future thinking reflection as we close here.
Yeah, that's a great question. So one of the things that I think about the most with the development of these technologies is public health. Is, right now the technologies are on the wrists of people who can afford them. But the promise of being able to monitor health on a large scale and bring it outside of a physical clinical setting, such that people who maybe can't afford to travel or aren't able to physically travel to a clinical center can still be under the surveillance of clinicians. So one of the things that I'm most excited about is thinking about how we can integrate these technologies into the broader, not only medical ecosystem, but healthcare ecosystem, making sure that we have preventative measures in place. And so that is a combination of different types of tracking modalities. There are now wearable sensors that also do biomolecular monitoring that can measure glucose, lactate, sort of a variety of different sweat biomarkers, for example. So I think that the possibilities are really endless, and part of our challenge is learning how to make these scalable, affordable, and interpretable so that we can all use them.
Thank you so much, Dr. Dunn. It was a fascinating talk. Thank you to everyone for attending. Once again, the event is CPD credited. So if you want to obtain your credit, you can please complete the evaluation form. And Matt, if you want to put up the QR code, there's a link there as well. We do invite people to please follow T-CAIREM on Twitter, join our T-CAIREM Hive, which is an online community, as it's now one of the biggest AI and medicine networks in the world. And we're delighted for you all to be a part of it. Thank you so much, everyone, and hope you have a great rest of your day. Thank you again, Dr. Dunn, for an amazing talk.